Untitled episode. Now is the 99th video and it's perfect for discussing this question. Our question here is about the digit sum of numbers. The digit sum is an apparently simple function, yet it can produce complex dynamics. Oh, my cat's meowing. Sorry for my cat, but this digit sum, when applied over and over again, is actually the process of an ancient calculating check method called casting out lines. The first part of the question asks us to find the integers below 100 that have a digit sum of 8. The first one is of course 8. Then we use our number bonds, you know them, 17, 26, 35, so we're literally going back into primary school. 44, 53, 62, 71, 80. In total, there are 9 integers. So let's n be an integer less than 10. How many integers are there with digit sum n? So let's try with digit sum 0. Of course 0. Let's write it in a triangular format. Then we have 1 and 10, 2, 11, 20, 3, 12, 21, 30. See? Writing the numbers in a triangular pattern makes this a lot more helpful because it just makes it more helpful. That's what math is for. Math is about making things more helpful. And so the digit sum will be n plus 1. And how about the integers with up to 1000? So think of the numbers in 1000 as a 10 by 10 cube. We don't have a large cube here. But imagine I'm holding a great big invisible cube. So let me put down the marker first. So imagine I'm holding a great big invisible cube. Now I'm holding two sides of it. Now I'm going to rotate it. Then I'm going to stretch the corners so you can see the digit sums more clearly. You know what it looks like? It's actually called in mathematics a triangular trapezohedron. Let me draw that out for you in case you had trouble seeing giant invisible cubes turning into triangular trapezohedra. Let me draw one out for you. And there will be another two faces behind this. Now, how about it? So n less than 10. So let's write it out in the pyramid form. 0. Then for digit sum 1, we have 1, 10, 100. For digit sum 2, we have 2, 11, 20. Right here, you see, it goes on the triangle. Then 2, 101, 200. And then 110. So we have 6 numbers. Now, what is this? It's the formula for the triangular numbers. So what we need to find is the n plus first triangular number. Luckily, it has this little formula for you, which I suspect you should memorize. Now, our next question only concerns the numbers greater than 500. So 500, and we need to find the sum. Find how many numbers are greater than 500 and have the digit sum of 8. So let's write the smallest one down. 503, 512, 521, 530. Then 602, 611, 620. See a pattern here? So that you each have 4 integers here, 3, 2, 1, and then you add them up. You have 10 integers. Now, if this problem was relaxed and only allowed at least one digit to be greater than 5, need not be the hundredth digit, I realized that I can also change the tens digit to be greater than 5. So we have 4 plus 3 plus 2 plus 1 equals to 10. And then same for the ones digit. And then we have 30 integers. Now here comes the crowning problem of the question. Find all the digit sums of the numbers from 1 to 1000. Now I know this is not a Gauss summation, but it's not Gauss. So let me write down all the possible digit sums. What is the smallest possible digit sum? 0, of course. So I'll be writing down my code digits for 0 to 27 to make things simpler for me to write. 0, 2, 3. Hang on, while this is playing, you can go watch your phones or there's a commercial break, watch the commercials. Anyways, I'm not writing code digits now, I'm just writing normal decimal numerals. Whoops! Then we have 26 and 27. We just write it down here. Now, we see 1, 3, 6, 10, 15, 21, 28, 36, 45, and 55. And from 10 to 17, things get weird. Now let us write down the digit sums in the other end. It's also trivial, just the triangular numbers, without any frills. And what is this? What's this great big space of 8 in the middle? In the triangular trapezohedron analogy, it's this space in the middle, the kind of meso space, which encompasses both triangular pyramids. Now, do you want to make a triangular trapezohedron at home? Well, we all love polyhedra, no big deal, just make one at home. And I hope you will be able to make the trapezohedron big enough to write down numbers on it and solve this problem. Now what's this big meso space in the middle? So let's consider a hypothetical decimal variant where the digit sums are 10. Let's call our 10-digit DEC, and it looks like this. Obviously, in normal decimal this won't exist, but we do it just for the fun. So there are 66 theoretical numbers which can fit in here, but since normal decimal doesn't have this DEC digit, so it's 66 minus 3 times 1 equals to 63. Same with 11, 12, and 13. And then you subtract our respective triangular numbers. 63, 69, 73, 75. And since this is symmetrical, these are exactly the same numbers as here, but reversed. Now let us calculate the sums from 1, 3, 6, 10, 15, 21, 28, 36, 45, 55, 63, 69, 73, 75, the interrupted triangular number sequence. As you can see, this sum, if you want to calculate it, it will have value 500. And if you don't, maybe you can plug it in your calculator again. Now, we have 500 of these little guys. And since we have digit sums ranging from 0 to 13, we can actually fold this so that we have 14, 15, 16, 17, sort of how the Gaussian approach to doing this. Now, realize that the digit sums all add up to 27. So the total digit sums of 500 times 27 equals to 13500. Remember I said this is the 99th video? Well, 99 is the only integer below 100 that has digit sum 18. See, even my cat agrees. Anyway, 13500 is the digit sum for all the numbers from 1 to 1000. You can also generalize it to other number bases like octal, hexadecimal, dozenal, or whatever number base you fancy. Well, as a homework exercise, do the same question. Actually, the crowning question, do the crowning question in your preferred number base. If you haven't heard of number base before, don't do binary or ternary, it's too easy. Well, in fact, I'll just do the binary case for you right now. So you have 0, 1, 2, 3, 4. So you only have 4 possible digit sums. So for 0, you only have 1. And then for 1, you have 1, 1, 0, 1, 0, 0, so you have 3, 3, 1. Simple, right? So, we can do something fun. Now it is 3 times 4 equals to 12. So you need 12 ones to represent the binary numbers from 0 to 7. Yep, you heard me right. Surprising. That's maths. Live with it. Even if you require 13500 digit sums to make all the numbers from 1 to 1000, live with it. It's maths. Huh? Anyway, thanks for joining me in this really confusing time, and have fun making your own triangular trapezohedron. Goodbye!